linear map of vector space from this quotient to the span of all Fourier modes of our vertex operators, just defined by such a formula. And then we've shown that this operation is indeed well defined. And just as a linear map. And then we've defined the bilinear operation on our vector space by such a formula, where here there is an index n, which comes from the vertex operator algebra structure. And these brackets are coming from our construction of U prime. And the lemma we've just proved is that the operation is well defined. So if we take the quotient, we take the image of our operator, and then we pair it with bk, we get 0. Okay. So let's proceed. So actually, let me explain why do we have this U prime over there. So another variant is as follows. So we define U of V to be the quotient of V tensor C of t modulo the same operation. Like this. Okay. So the only difference is that instead of taking just polynomials in TT inverse, we're taking Laurent series. So C of t is some okay. And so this is our U of V. Good. So now we want to define the same operation, namely again A M BK. Let me put it as a lemma. Formula AMBK equals sum n greater or equal to 0, Mn, and AN B M plus K minus N is well defined on U. So what do we have to show? So what's the point of this lemma? Yes. So in principle, now we have to take F, which is the sum, say, F M A M. And G, sum GK, BK, here over M. And then we need to show that FG is well defined. So because you see, these are infinite sums. And in principle, there might be infinite sum of numbers. Right? So we need to show that the commutator of f and g makes sense. Okay. Yes. Let's see. Mhm. Uh-huh. Sorry. Well, did I? Sorry. So indeed, so if we write this as sum, yes, so it's sum over n greater or equal to 0, and then we put mn and a and b, and then we put, say, r minus n, and the summation runs over all r in z, and here we have the coefficient is sum f m gk, k plus m is r, correct? Does this make sense? Okay, let's rewrite it a little bit. So actually, the result should be so this is how it is written now. Now let's write it as follows: the sum over all r, where r is morally m plus k minus n. Okay, and r equals, you see, r m plus k minus n. Yes, so if here we have m greater or equal than n and k greater or equal than n, well, n is just a number, negative or positive. So this r is so what is, yeah? Well, maybe I actually, sorry, maybe I wrote it the wrong way. You see, the problem is that so this so this is the wrong way to write it, yeah, because this A does not have to be the same for all elements, right? So I mean, so once again, what is our so what is our element? Yes, so our element is Fm times A M T to the M, right? Yes, all AM are elements in. Ready? And then G is sum M greater than OK greater than N. And we put G K and BK T to BK in so on. So we take because so they okay. So you see, this is the notation, yeah. So you take A from B, and you multiply with T to the N. Now it's just a number. We can. You're absolutely right. Yeah. Okay, now what is the operation? Maybe then you're right. So let me put F here and G here. Sorry. Okay, so how does it work now? So F G is the sum over MK greater than N. And then what do we take here? Sum N greater than 0. Mn F GK. And now if we fix R Right. Yeah. Mhm. So R, and then we put T to the R. Let's see. And then N equals to, so M plus K minus N is R. Mm-hmm. No, I'm sorry. Well, no, well. So what is our vector space? V tensor C of T. I'm sorry. What is the definition of this vector space? You should have corrected me. So what is this? Yes. So what does this mean? So this tensor product has a basis, and it's a finite combination. The elements of this vector space are finite combinations of the expressions the following form. The expressions are A from B. We take A from B, and we take F from C of T. Okay, and then we write A tensor F, and then we take finite sum of expressions of this sum. So I wrote this correctly from the very beginning, but then I decided that I wrote it wrong, and you didn't stop me. Yes. So well. So the proof. Well, since so just maybe I write one thing that we have to check that have sum F. So A. Yes, and A tensor so Fm, where Fm is a number, A T to the N. So Fm is a number, and A is from B, and we need to take G. So now this is what? So this is the sum M K greater than N F M G K and sum N greater than 0 A N N A and B T to the M plus K minus. Right. And actually, indeed, so the sum is from 0, we can put to the same N. Well, I mean, you can choose maximum. And this means that so this indeed belongs to okay. Sorry for the mess. Okay, so now so the important thing is that we have the following theorem saying that u of v, let's do the u prime, but u of v as well, are Lie algebra section with respect to the breaking. U of v and so the proof, so what do we have to show? We have yes, a n like this, and the Jacobi. Okay. So actually there are two ways, brute force computation and an intelligent way. So let us start with the brute force computation, then we'll maybe will not finish it completely, and then we'll discuss how to prove it in a more I would say. Say it again. Because so just just let's see what does this mean. Yes, so what do we actually have to prove? If one do it naively, yes. So we just need to show that the sum n greater than 0. That's the proof. Mn and then a and b m plus k minus n should be equal to minus sum. Yes. So how, indeed, what should be, what can we use to prove this? But should it be exactly like this, or yes? So this is actually important point. So this should be modulo the image of C times identity, right? But actually, there should be some way to compare Bn of A and An of B. So is there some? It's so important. Yeah? So y of A, Z, B equals to what? Mm-hmm. So this is the skew symmetry, yes? So what does it actually mean? Sorry? No, but we can write it. So we can write that. So sum a and z minus n minus 1 b equals the sum L greater than 0 t to the L over L factorial t to the L and the sum b n minus z minus n minus 1. I'm going to put a bk here. So then let's see. So what does it mean that A and B equals to what?
-1.
Like this, right? Okay, let's do this. Like this. So this is the formula. Yeah? So it looks a bit strange, but still. So it means that the result of application of AN to B is written as a series, infinite series, such a way. Now, so this is our formula. And what we want to prove is, okay? So we should insert this gadget here. L plus n minus 1 to the power L plus n plus 1. Okay. So we should insert this gadget there, and then what we get is the insert to the first line. Oops. Okay. And then what we get there is right. So A and B, n plus k minus n, is sum L greater than 0, 1 over factorial, and then you have GL, BL plus n, A, m plus k minus n. Okay? then how to work with this? So how to somehow, well, we have to compare it with the right hand side, but there is this yes. Okay. So how to rewrite this guy? So we want to rewrite this one using this modular. What are we using? We are using. So we are using the quality that TA something equals minus something TA. Oops. Yes. Minus yes. Mm-hmm. So what are we getting here? And this here is. It comes here. And what do I put here? No, but we are dropping this number. Ah, okay. Okay. Well, to be precise, so we put sum and it's 0 and n. So, but at least, so this looks a bit complicated, but at least these are exactly the terms we have on the right hand side. So there will be a funny quality for binomial coefficient. So actually, this claim that this formula equals to the right hand side of the upper formula. So actually, if you look at this, so you'll get some equation, and it's easy to put. Okay. So this. Well, a little bit. So let's try another approach. Mm-hmm. Well, you see, actually, this is what when we were doing the vertex algebra, then here we know that there is a skew symmetry and Jacob identity. But this is not kind of not obvious at all, right? So I mean, no, I mean, yeah, I mean, such a formula is not obvious, yeah. So the point is that you are getting actually the Lie algebra is absolutely not clear. So, I mean, there is no obvious way why this should be true. And actually the answer to your question is that the minimal possible relation we have to apply are these ones. So if we don't, we're not getting Lie algebra. But if we do apply it, we are getting Lie algebra. But you can't get it for free. Yeah. Huh? Mm-hmm. So you want this U prime of V to be exactly the span of Fourier modes of your vertex algebra. Is that what you are asking for? This might be possible, probably, but we want the claim is that for any vertex separated algebra, так я думаю, слишком. Да. So another approach So the approach is as follows. So let's get back to our vertex separated algebra V. And so we have a structure of vertex separated algebra here on V. And then we tensor it with the C of TT inverse. And let's consider the structure of vertex separated algebra on this space. So let us endow C of T inverse with the structure of VOA. So for this, we have to define what is y of t to the m z. So do you have any suggestions? So structure of actually abelian vertex separated. But what do you mean? Abelian means that all our fields do commute, literally commute, without multiplying by z minus w. What, z to the minus m? But what does it mean? What does such a formula mean? So this should be serious, yes? No, it's too trivial. I mean, it does not feel any. I mean, I'm not sure this would give you. I don't think it would give you a vertex separated algebra structure at all, but. No, the size is as a vector space is this one.
by just multiplication.
Multiplication with what? By what? It's a good idea, but what should be multiplication by what?
We have some vector to say a which is
No. This. No. This vertex separated algebra on this space. Good. No, but shifted. So there's a good. So actually, it's a rather conceptual point because so what do we have here? We have z, which somehow can be seen as a variable. So usually we were thinking about this as a formula variable, but here you have t and you have z. So why don't we shift? But shift, just literally shift. So take t plus z to the n. So this, yeah, because so after all, vertex operator, just an operator on kind of, well, I mean, something depending on z in principle. And this OPE is then we were saying that z and w are somehow close, and we were considering the expansion on the diagonal. So there is some way, some reason to think of z as a variable, so sitting on a complex plane or on a torus or whatever. So here, this is kind of very trivial, but somehow very concrete example. So where we can consider z as a variable and just shift. So what does it mean? Let's expand. So what should I write? Okay. So does this make sense? But let's see, does it, what? I don't like this formula. Well, do you? There's some reason why this formula is very strange. And even not strange, even wrong. Yes, but how do we interpret this formula? Say it again. Does not work this way, yeah, because so if we apply it, why? But we could have taken it -1, say -2. No, just yeah. Mm-hmm. So why don't you like it? So the claim is that, so we claim that this is this formula defines the VOA structure. Well, I don't know. So you suggest just to erase this one, but then this won't work. Why they find it? What do you find it in what direction? Yes, but you remember that actually let me put as a remark. So we proved that if VOA is abelian, then all fields are regular. Mm-hmm. Mm-hmm. So it's important that abelian Lie algebras are very simple. Abelian vertex separated algebras are very simple. They have no singular part at all. And this is how it works. Let's see. Yes, T. Like this, I think so. Say T is just dt. Yes. Minus, where do you want to put -1? I don't understand, so please.
I just, because you said that everything is defined by this, so I want to.
Okay, so let's see, what's that? So you put n is 0. So this is n is 0. Yes, just multiplication by t to the.
And 0 to I. And what is your point?
So the So actually, this is the formula. Okay, with t is dt. And actually, it's just the explicit form of this formula. But well, I have dt here, but I think it is like this. So if you want to get binomial coefficient, I think like it's exactly like this. No, what?
Нет, у нас было в начале лекции, сказали, что вот Т, оно как бы
Well, I mean the yes, so the equality. So we have this is x as 0, yes, but we have this an action of tensor product of two things. So it's not like you are saying that T is dt. This T works on vertex separator algebra V, and the dt acts on the C of TT inverse. dt, because this should be T should be an operator on our space, and our space is C of TT inverse. Yes, that's true. That's true. But the action on the field commuted comes from the action of the vector space. So the meaning of these two variables T and Z is different here. Yes, Z is a formal variable used for combining all the operators, and T is the variable from our vector space. Okay, so now we have a vertex separator algebra structure on C of TT inverse. Now we obtain a V or a structure on V of T. Exactly, yeah, it's what we are doing. So y of a t to the n z equals to y of a z tensor y of t to the m z. Sorry? And this is the general, I don't remember if we've discussed it at some point, but this is just a general statement that if you take the product of two vertex separator algebras, then this again a vertex separator algebra. Did we discuss it? Maybe I have skipped it, but again, if you have two vertex separator algebras, then you can organize the tensor product of two vertex separator. So maybe if I didn't say it at some points, but write this again or one first time. Maybe I. No. It's a tensor product of operators. What is correct is that the operator T equals to T tensor 1 plus 1 tensor T, which is dt. Mhm. Absolutely. Yes. Mhm. Mhm. Absolutely. That's right. So, if say W and W1, W2, two vertex separated algebras, then their tensor product is a vertex separated algebras. In particular, the vacuum for the tensor product is the tensor product of vacuums. Okay. So we are actually left with the vertex separated algebra. So now we consider W to be the tensor C of TT inverse, and our U prime of V is W mod image of T. Okay. No, I'm rephrasing it. We are doing it because otherwise we do not have skew commutativity. So, no, our initial point was that the operator T produces the relation that AN is minus N TAN is minus N AN minus 1. Okay. So this is just a relation in any vertex separated algebra. And therefore, if we want to have a chance to mimic such a situation, formally mimic, yes, so replacing this round bracket by formal square brackets, then we need to introduce such a relation. Otherwise, it doesn't work at all. No, it's yes. No, it's important that we are working with this situation, not a kind of general construction. This might be an interesting question, yes, but here this very particular point. Well, because this T is actually this operator. No. You're asking in general, does it make sense to quotient a vertex separated algebra by the translation operator? I don't know, but well, there might be some point, but I don't know. This might be, maybe it's good to think about this. I don't know, but here there's a very particular reason why we are doing this. So this T is something very concrete. Okay, let us finish with one computation in order to connect the problem we started with. So what is, please let me know, we take AT to the M, and we take the zeroth component. We apply it to BT to the K. From W. Just a vector. So what is this? So what's the result? Can we use the letter N for the summation? Yes, N. N greater. And say it again. Just let's substitute. So we know what is the, this is the formula, yes? And this is the formula. Why don't we substitute it there? But let's just write it as a sum over N. N, we have this N there.
Apply 80. Can we immediately apply 80?
Say it again.
Can we immediately apply 80?
A is a vector from V, and B is also a vector from V. So we can't apply a vector from V to a vector from V. And we can apply to B, yes, sure. Yes. ATM is a vector from W. Yes. Well, Y of ATM Z is the sum. ATM R, overall R, Z minus R minus 1, which means that, which is explicitly given by the sum A S Z minus S minus 1 times sum n greater than 0 M n Z n G m minus n. Okay. So this means that ATM 0 is what? We want n greater than 0. Yes, and n minus s is 0, right? Yes, R is 0. Okay. So we need n equals s. Okay. So then, can you tell me what do I have to write? Say again. No. Do you recognize this formula?
Oh, it's just complete.
It is. Yes. So actually, do you see, let's look at this formula here. So now just you were asking why do we mod out by T? So now let me stop now. But so the rest is going to be your homework. I mean the proof of the skew commutativity and Jacobi identity. But I'm saying that after this formula is proved, after we recognize this commutator which is just the result of application of one thing to another. It's almost, of course, using this skew symmetry property. Yes. Yes. Yes, so actually what we are doing, we are passing from the tensor product of vector space to one vertex separated algebra. Then we can use our vertex separated algebra machinery, for example, this skew symmetry, to work with this. Well, it depends what we want. So I mean, well, important thing is that we have this W as a vertex separated algebra. So this is important. In principle, yes, but you see what we want to prove very concrete thing. Yes, so to prove that our bracket is skew symmetric. Yes, we need to show that if you replace this one. Yeah. Mm-hmm.
Some ways to make them not using if we have some additional structure. For example, if our separator algebra has the representation of the first separator algebra, the space of the second. For example, if we have да, можно
Можем делать полку, может, да, здесь. Это такое, что правда можно дать, а если одна здесь другой, можно преимущество.
Да, абсолютно. No. So if you have a so if you have a vertex separated algebra and vertex separated subalgebra, then you can take the quotient of one by another if it is a vertex separated ideal. But this might not be no, actually, I don't know an analog for the semi-direct product of groups, but there is something. Well, in principle, there might be. You might think about the taking quotient vertex separated algebra by an ideal as a kind of such an operation. So you find the sub algebra inside the larger algebra, and then you take the quotient. But I don't know if this is exactly what you were asking about. Well,
quotient,
yeah.
and ideal, subalgebra,
Mhm.
and the algebra we start from is somehow perfect.
I see. No, I think there should be something of this sort, but I can't spell out it rigorously. Further questions? Okay, if not.